Hello everyone, I'm Yang Zhang from the MIT IBM Watson AI Lab. I'm going to introduce our work on global rhythm style transfer without text transcriptions. To start with, let me first briefly explain what is style transfer in speech. Style transfer in speech refers to a set of tasks which, given a source speech and some target domain information, produces a converted speech that resembles the target domain in terms of style, but retains the content of the source speech. Depending on how the domain is defined, the speech style transfer problem can be broken into different subtasks. For example, if the domain corresponds to different speakers, then the task becomes voice conversion. If the domain corresponds to different emotion categories, then the task becomes emotion style transfer. In this talk, we will be focusing on non-parallel style transfer, which assumes no parallel data across the source and target domains are available during training. Despite the recent rapid progress in this field, non-parallel style transfer algorithms still suffer from one important limitation. To see this, let me show you a voice conversion example, where the source and target speakers have completely different speech rates. Here is the source speech,
6 spoons of fresh snow peas.
which is pretty slow. Here is an example utterance of the target speaker,
5 thick slabs of blue cheese,
which is pretty fast. Now, let me show you the conversion result of one recent voice conversion algorithm, AutoPST.
6 spoons of fresh snow peas.
As many of you may immediately notice, AutoPST only converts the timbre to the target speaker. Despite the drastic difference in speech rates, the rhythm in the converted speech remains largely identical to the source speech. This example reflects the broader challenge of disentangling rhythm in speech style transfer. Although some algorithms start to address the problem, many of them will rely on the availability of either some parallel data or text transcriptions. Without either of these additional information, the problem remains very challenging and largely unresolved. In particular, our previous work, Speech Split, has made a sizable step towards disentangling rhythm in an unsupervised manner, but it requires ground truth rhythm information from the target speaker in order to do the conversion. In this talk, we propose AutoPST, which is among the first algorithms that can successfully convert rhythm without parallel data or text transcriptions. To give an idea of how AutoPST performs, here is the AutoPST conversion result of the aforementioned example.
6 spoons of fresh snow peas.
As we can hear, both the timbre and rhythm are successfully converted. Before I describe how AutoPST achieves this, I would like to take a moment to explain what we actually mean by rhythm information. Suppose a speaker wants to utter a word, say cat. Notice that cat consists of 3 phones, forming a phone sequence of length 3. We refer to such phone sequence information as the content information. Now, let me use blocks of different shades to represent a speech frame uttering each of the 3 phones respectively. If a slow speaker were to utter the word, he or she would produce a frame sequence like this, where each phone is repeated for many frames. If a fast speaker were to utter the word, each phone is repeated for fewer times. Such information about how each phone is repeated across frames is what we refer to as the rhythm information. It characterizes the speech rate, pause, and other rhythm patterns of a speaker. Under this perspective, the goal of disentangling rhythm translates to retaining the phone sequence information while obscuring the repetition information. To achieve this goal, AutoPST adopts the following framework. Similar to the AutoVC structure, it contains an encoder, which encodes the input speech feature into a hidden representation, and a decoder, which tries to reconstruct the input speech. The major difference from AutoVC is that AutoPST contains a third module called the Resampling module, which attempts to scramble the rhythm information by temporally resampling the hidden representation. In this way, the decoder would have a hard time guessing what was the repetition of each phone before the resampling module. So the next question is how to set a resampling algorithm so that it can effectively obscure the rhythm information. To answer this question, let's revisit the cat example. If we observe the two utterances more carefully, we can see that the phones are not stretched or squeezed uniformly. In fact, it has long been observed that when speech rate changes, the vowel lengths tend to change more than do the consonants. In this cat example, the repetition of the vowel a changes very significantly, but the other two phones barely change. This implies that steady segments in speech, like the a segment in our example, would have a larger elasticity. Therefore, in order to truly confuse the decoder, the resampling module needs to mimic this behavior. Motivated by this, AutoPST introduces a similarity-based downsampling algorithm that consists of 3 steps. First, we need to come up with a measure that gauges the content similarity between any 2 frames. In other words, ideally, frames with similar phonetic content should have a high similarity, while frames with different phonetic content should have a low similarity. There are many ways to measure this. In our implementation, we adopt the measure proposed by Body et al., which has been successfully applied to unsupervised speech segmentation. With this similarity measure, the next step is to go through the speech frames one by one and draw a segment boundary if the similarity between the next frame and the previous segment drops below a threshold tau, as denoted by the red bars on the slide. After segmentation is complete, the final step is to collapse each segment into one representation by mean pooling. As can be seen, the downsampling algorithm ensures that the steady segments get compressed most. As you might have noticed, the segmentation threshold tau plays an important role here. If the threshold is high, namely close to 1, there will be many segment boundaries, and the downsample sequence will be long. If the threshold is low, there will be fewer segment boundaries, and the downsample sequence will be short. In order to scramble the rhythm information even more, we introduce a random thresholding procedure, where at each frame, a random threshold is drawn. As a result, the downsample sequence will have some segments that are more compressed than the other, making it even harder to guess the original repetition information. So far, I have only talked about downsampling and the threshold tau being smaller than 1. In fact, this procedure can be extrapolated to upsampling with the threshold tau going above 1. The generalized procedure becomes as follows. We will still go through the frames one by one. If the random threshold is below 1, we perform the aforementioned downsampling scheme. If it is larger than 1, we do 2 things. First, we immediately add a segment boundary. Second, if the similarity of the next frame and the previous frame is high enough, we insert yet another segment by copying the previous code. After this segmentation process is done, we follow the same mean pooling procedure to get the resample result. As can be seen, because of the insertion of the additional segments, some parts of the sequence get upsampled while others downsampled. Nevertheless, in both the upsampling and downsampling cases, our similarity-based algorithm would ensure that the steady segments get stretched or compressed most significantly. This is all for the resampling algorithm, but the resampling module alone is still insufficient to remove rhythm information. This is because, in practice, we find that the encoder and the decoder would always try to figure out alternative ways to communicate the rhythm information. In order to break such collusion, we introduce a 2-stage training scheme as follows. In stage 1, called the synchronous training, we add a realign module that restores the repetition information so that the encoder and the decoder would not find it necessary to collude on the rhythm information. After convergence, we switch to the second stage, called the asynchronous training, where we remove the realign module and then fix the encoder. In this way, even though the two players would have the incentive to collude, they are not able to because one of the players is fixed. We perform a set of experiments to evaluate AutoPST's ability to disentangle rhythm. We strongly encourage you to visit our demo webpage for more results. In the first experiment, we picked two groups of speakers. One is very fast and the other is very slow, and then perform voice conversion between the two groups. Here is an example of slow to fast conversion. Here is the source speech.
5 thick slabs of blue cheese.
Here is the target speech.
The rainbow is a division of white light into many beautiful colors.
We compare three algorithms: AutoVC, which we already know would not convert rhythm; random sampling, which is similar to our AutoPST algorithm, except that the resampling is not based on similarity, and then our algorithm. Here is the AutoVC result,
5 thick slabs of blue cheese,
which is as low as the source speech. Here is the random resampling result,
5 thick slabs of blue cheese,
which is slightly faster. Here is the AutoPST's result,
5 thick slabs of blue cheese,
which is almost as fast as the target speaker. Let's switch to the fast to slow conversion. Here is the source speech.
5 thick slabs of blue cheese.
Here is the target speech.
The rainbow is a division of white light into many beautiful colors.
Here is the AutoVC result,
5 thick slabs of blue cheese,
which is undesirably fast. Here is the random resampling result,
5 thick slabs of blue cheese,
which is slightly slower. Here is the AutoPST result,
5 thick slabs of blue cheese,
which is almost as low as the target speaker. To objectively measure rhythm conversion, we pick some utterances in the test set that are uttered by both the fast and the slow speakers. For each fast-slow pairs, we measure the duration of fast to slow conversion and slow to fast conversion, and compute their relative duration difference, or RDD. The intuition is that if the rhythm is converted, then fast to slow conversion should be longer in duration than the slow to fast conversion, so the RDD should be positive. If rhythm is not converted, RDD should stay negative. Here is the box plot of the RDDs across all the test parallel speech pairs. As can be seen, only AutoPST has largely positive RDDs, and the RDDs of the other two baselines are negative. In other words, only AutoPST can significantly change the speech rate to match the target speaker. We also performed a subjective evaluation where the subjects are asked to assign a score of 1 to 5 on the similarity to the target speaker in terms of each of the following three aspects: timbre, prosody, and overall. The results show that AutoPST conversion has the highest subjective similarity in all three aspects, particularly the prosody aspect. So far, we have only verified that AutoPST can change the overall speech rate, but rhythm information is much richer than just the speech rate. We would therefore like to know if AutoPST can capture more fine-grained rhythm patterns. To test this, we artificially create some abnormal rhythm patterns and see if AutoPST can correct it. Specifically, here is the original normal speech.
One showing mainly red and yellow.
We can hear that the last word is yellow. Now, we create an abnormal rhythm pattern by stretching the word yellow, like this.
One showing mainly red and yellow.
We then use different algorithms to reconstruct the input speech. If the rhythm disentanglement is thorough, such an abnormal rhythm pattern should not leak into the hidden representation and should not appear in the reconstructed results. Here is the result of the random resampling baseline.
One showing mainly red and yellow.
As we can hear, it does try to fix the overall speech rate by squeezing the utterance, but it is unable to reduce the duration of yellow more than the other words. Here is the AutoPST result.
One showing mainly red and yellow.
The abnormality is greatly alleviated, which verifies that AutoPST can disentangle rhythm information beyond just the overall speech rate. That is all for my presentation. To sum up, we introduce AutoPST, a speech style transfer algorithm that can convert rhythm. To achieve this, AutoPST adopts a similarity-based resampling module to scramble the repetition information, and a two-stage training scheme to prevent the collusion between the encoder and the decoder. Our experiments show that AutoPST is effective in disentangling rhythm, including the overall speech rate and more fine-grained rhythm patterns. With that, I will conclude my presentation. If you would like to find out more about this work, please visit our demo webpage and read our paper. Thank you very much for your attention.